Imagine a world where everything you touch, everything you see, everything you are, simply vanishes. A world where the very elements that make up your existence, from the iron in your blood to the gold in your jewelry, never formed. Sounds like a dystopian nightmare, doesn't it? But what if I told you that our entire reality hinges on a cosmic ballet of destruction and creation, a process so violent, so utterly cataclysmic, that it's almost beyond human comprehension? And what if the most vital ingredients for life itself were forged in unthinkable collisions? Events so rare and so powerful, we're only just beginning to grasp their true significance. To truly understand this profound cosmic secret, we first have to rewind the clock, not just hundreds, but billions of years. Picture the very dawn of our universe, a time immediately following the Big Bang. This nascent cosmos was a remarkably simple place. It was almost exclusively composed of the lightest elements, hydrogen and helium, with a tiny trace of lithium. Our periodic table, with its rich tapestry of iron, oxygen, carbon, and all the precious metals, simply didn't exist in any meaningful quantity. This presents an enormous cosmic riddle. If the universe started with such limited ingredients, where did everything else come from? How did we get the astounding chemical diversity that makes planets, people, and everything in between even possible? For decades, scientists puzzled over this fundamental question, knowing that the answer held the key to our very existence. They knew stars were involved, of course. Stars are the universe's primordial alchemists, fusing lighter elements into heavier ones in their scorching cores. But that alone wasn't enough. Something else, something far more extreme, had to be at play to create the truly heavy elements, those beyond iron on the periodic table. The universe held a dark, violent truth, waiting to be unearthed, a truth about the forgotten collisions that shaped everything we know. For a long time, the prevailing theory was that supernovae, those spectacular cataclysmic explosions marking the death of massive stars, were responsible for forging all the heavier elements. And indeed, supernovae are powerhouses. They create elements up to and including iron in their cores, and during their explosive death throes, they can even synthesize some elements heavier than iron through a process called the R process, or rapid neutron capture. This occurs when an avalanche of neutrons bombards atomic nuclei, quickly building up heavier isotopes which then radioactively decay into stable, heavier elements. It was a good theory, a compelling one, explaining a significant chunk of the universe's composition. But there was a problem, a persistent, nagging inconsistency in the cosmic accounting. The numbers just didn't add up. Supernovae, while potent, couldn't account for the sheer abundance of the very heaviest, rarest, and most precious elements found throughout the cosmos, elements like gold, platinum, and uranium. These elements, essential for both our technology and our understanding of nuclear physics, seem to require an even more extreme, neutron-rich environment than supernovae could provide. It was a missing piece, a cosmic ingredient list that was still incomplete. The universe, it seemed, had a deeper, darker secret tucked away in its most violent corners. Scientists began to theorize about exotic, hyperdense compact objects, the remnants of massive stars that had collapsed under their own gravity, but weren't quite massive enough to become black holes. These are neutron stars, objects so incredibly dense that a sugar cube of neutron star material would weigh billions of tons. Imagine that. These are literally stellar corpses, celestial husks packed with matter, compressed to densities beyond imagination. And the theory went, if two of these incredibly dense, rapidly spinning objects were ever to collide, the resulting inferno, the sheer gravitational violence, might just be enough to bake those missing heavy elements into existence. This was a theoretical leap, a hypothesis born of necessity. But how could we ever hope to observe such a rare, distant, and unbelievably fleeting cosmic event? For decades, it remained a tantalizing, yet unconfirmed whisper in the astronomical community, a grand conjecture on the edge of scientific understanding. The tension built as the search for this ultimate cosmic forge continued, a search that would eventually lead to a revelation that profoundly altered our perception of the universe and our place within it. The stage was set for a discovery that would rewrite the textbooks and redefine the origins of everything precious. Then, in August of 2017, the universe decided to show its hand. On a quiet Monday morning, half a world away from the initial detection, the LIGO and Virgo gravitational wave detectors, instruments designed to sense the most subtle ripples in the fabric of spacetime, simultaneously detected a signal unlike any they had ever seen. It wasn't the familiar chirp of two black holes merging, which they had previously observed. This was different, a unique signature. Immediately, within seconds, astronomers worldwide were alerted. What followed was an unprecedented global effort. Telescopes, both on Earth and in space, swung into action, pointing towards the detected signal source in the galaxy NGC 4993, approximately 130 million light-years away. Within hours, the optical telescopes began to see something truly extraordinary. A new, incredibly bright kilonova appeared in the sky, an explosion that was 1,000 times brighter than a typical nova. This wasn't just any explosion. Its spectrum, its light, was unlike anything ever witnessed before. For the first time in human history, we had observed the direct aftermath of two neutron stars colliding in a cosmic ballet of ultimate destruction. This wasn't a supernova. This was something far more exotic and infinitely more potent for element creation. As these two unbelievably dense, rapidly spinning neutron stars spiraled inwards, their gravitational dance accelerated, creating monstrous ripples in spacetime that traversed the vast cosmic distance to eventually brush past our planet. The final moments of their existence were an unfathomable maelstrom of matter compressed beyond comprehension, a furnace where temperatures spiked to billions of degrees and pressures were unimaginable. In that fleeting second of ultimate collision, as the two stellar corpses merged and then potentially collapsed into a new, more massive neutron star, or even a black hole, an enormous amount of highly neutron-rich material was ejected at relativistic speeds. This ejected material, suddenly freed from the crushing gravity of the neutron stars, expanded rapidly, triggering the most efficient and powerful R process known to exist in the universe. Imagine a cosmic shotgun blast, scattering a deluge of neutrons, bombarding existing nuclei, synthesizing moment by moment, element by element, all of the universe's missing heavy elements. Gold, platinum, uranium, thorium. They were all forged in that cataclysmic, fleeting moment. The light from the kilonova persisted for days and weeks, meticulously observed by hundreds of astronomers, each data point confirming the incredible hypothesis. The spectral analysis of the explosion's aftermath revealed the unambiguous signatures of these heavy elements, explicitly confirming their creation in this ultimate cosmic forge. The mystery was solved. The universe's full inventory of elements, from the hydrogen in the stars to the gold on our fingers, finally had a complete and coherent origin story. The forgotten collisions were, in fact, the hidden engines of cosmic creation, the violent midwives of precious matter. This monumental discovery, the direct observation of a neutron star merger, didn't just solve a long-standing astrophysical riddle, it reshaped our understanding of where we, as a species, come from. Think about it. The gold in your smartphone, the platinum in your catalytic converter, the uranium powering nuclear reactors. Every atom of these precious and vital elements was born in the fiery, violent death throes of two ancient neutron stars, billions of years ago, in a galaxy far, far away. Each piece of jewelry, every technological marvel, is literally infused with the remnants of these cosmic collisions, a direct lineage to the most extreme events the universe has to offer. Without these forgotten collisions, our planet would be far less chemically diverse, and perhaps even life as we know it, which relies on a complex array of elements, might never have emerged. Our very existence is a testament to the universe's capacity for both immense destruction and awe-inspiring creation. We are literally stardust, yes, but more specifically, we are the children of colliding neutron stars. This revelation opens up new avenues of research, prompting astronomers to seek out more of these kilonova events, refining our models of element formation, and perhaps even understanding the role these events played in seeding the early universe with the chemical complexity needed for planetary systems and life to flourish. The universe is a vast, mysterious place, continuously unveiling its secrets. And as we continue to listen to the whispers of space-time, what other forgotten collisions, what other cosmic alchemies await our discovery? What fundamental truths about our existence are still hidden in the depths of space and time, waiting for us to just listen closely enough?